Welcome, everyone. So we're going to do a little makeup for today's Miss class, and I want to start with continuity of elementary functions. So turns out most of the functions we're going to be looking at in this course, and then even into Calc 2 and Calc 3, they're continuous on their domains. And we have a little list, a little catalog here of the different basic functions we're going to consider. So I want to start with kind of the most fundamental, polynomials. And they're continuous on their domain. Turns out, actually, all of these functions are continuous on their domains. So just to be helpful to remember, what is the domain for a lot of these different functions. So polynomials, things like ax squared plus bx plus c, the domain is all real numbers. Rational functions are where you take a polynomial and you divide it by another polynomial. So same thing, all real numbers, or we can write that as an interval minus infinity to infinity. Now there is some exception here. So we have to be careful because we're dividing, we can't be dividing by 0. So there is an exception. And this is going to be kind of a recurring theme. Can't divide by 0. We also have root functions. So the domain of root functions depends on whether this is an even root or an odd root. So if it's like a square root or a fourth root or a sixth root, then we can't plug negative numbers in. So the domain is the closed interval from 0 to infinity. If this is an odd root, like a cube root or a fifth root or something like that, then all real numbers work for that one. So the interval minus infinity to infinity. Trig functions, sine and cosine, are probably our two most fundamental trig functions. Behave really nice. Their domain is all real numbers, so they're continuous on their domains. Tan x, same thing, all real numbers. Now, if we remember, we looked at tan x being equal to sine over cosine, so there is some division hidden here. So we have the same kind of exception, except where we divide by 0. So in this case, since tan is sine over cosine, we divide by 0 when cosine x is equal to 0. So these are, what are these? These are the odd multiples of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, all the different odd multiples. And then some of the other functions we're going to consider, we've got some inverse sine and cosine. So these are defined on the closed interval minus 1 to 1. And then we've got inverse tan, which is defined for all real numbers. So it's continuous at all of those x values on the x-axis. And then we've got our natural exponential function, similar thing. And then finally, the last kind of one that gives us an exception is this natural log function. And its domain is the open interval 0 to infinity. So out of these table, the three big things to watch for. Most of these, there's really no exception. It's all real numbers. The main one, we want to look for division by 0. So when we have a function, if you see a denominator, see a fraction, figure out where that denominator is equal to 0. Another one is for even roots. This is another exception. We can't have negative numbers inside an even root. So you want to look for any possibility in your function if you have negatives under an even root. That can also cause problems. And then the last one is this log function. So for log functions, you can't plug 0 in and you can't plug negative numbers in. So negatives and 0. In the log function. So those are the kind of the three main exceptions. But other than that, we do a little bit with inverse sine and cosine, so there is some restriction there. But these are primarily the three main ones we want to keep track of. Now, the thing is, we can take these kind of building block functions and we can combine them. And there's all sorts of different ways we can combine functions algebraically. And so we have a result that says, if we take two functions, f and g, and we know they're both continuous, well, we can add them, and the result is continuous. We can subtract them. The result is still continuous. We can take a continuous function and multiply by a constant. That gives us a brand new continuous function. We can multiply continuous functions, and the result is continuous. And we can even divide by continuous functions. But again, there's one exception to this one. We can't have division by 0. So this one we got to be a little careful of. But as long as we're not dividing by 0, then the result of taking two continuous functions and dividing is going to be another brand new continuous function. All right, so let's get a little practice figuring out where a function, what the domain of a function is, and then concluding where that function is continuous. So we've got this example 6 in our notes. We've got this function 3 times natural log x plus inverse tan of x, all divided by x squared minus 1. So the idea here is we're going to look at each of the components. We're going to try to break this function down into its elementary parts. So I'm going to rewrite this first of all, just a little bit of a rewrite. And rather than dividing by x squared minus 1, I'm going to think of this as 1 over x squared minus 1 times 3 natural log x plus inverse tan of x. So we can do this with fractions. We can take the numerator and just kind of peel it off and put it next to the fraction. That's all we're doing here. So when we look at this, what do we have? Well, we've got this 1 over x squared minus 1. That's a rational function. We've got 3 times the natural log of x. So this is the constant multiple of just natural log. And then we've got inverse tan. So the idea is we're going to figure out the domain of each of these functions individually and then try to figure out all of the x values that satisfy all three of those different domains. All right, so let's start with the easiest one. Let's start with inverse tan. This one's probably the nicest. All right, so what's the domain of inverse tan? So let's pop back up, go up to our table there, and inverse tan, all real numbers. So we'll just write that as an interval. Minus infinity to infinity, the entire x-axis. All right, so that's our inverse tan. So let's go to the next piece. 3 times natural log. Well, that multiplication by 3 isn't going to change anything, so we're really just looking at natural log x. That's really where our main focus is here. So what's the domain of natural log x? Well, if we go back up to our table, there it is. The open interval 0 to infinity. Okay. And then finally, we've got that rational function, the 1 over x squared minus 1. So it's a polynomial on the top, actually just a constant polynomial, constant function there. And then we've got a polynomial on the bottom. So where are these rational functions continuous? What is the domain of a rational function? Well, it's mostly all real numbers, so it's the entire x-axis, except where we divide by 0. So we are going to potentially have to throw some x values out. So it's going to be the interval minus infinity to infinity, and except where that term in the denominator, the x squared minus 1, is equal to 0. So let's figure out when, or even if this happens, by trying to solve that equation for x. So we're taking the denominator, we're setting it equal to 0 to see if we get any division by 0. And if we do that, if we solve this for x, we can add 1 to both sides to get x by itself. We could also factor. We could use quadratic formula on this thing. I think probably the easiest way, though, for this is just to directly solve it because we don't have too many terms. So we're going to solve it for x. And when we do that, add 1 to both sides. We get x squared is equal to 1. Apply the square root function to both sides. And whenever we apply the square root in a solution, we got to put a plus or minus in front. And then square root of 1 is just 1. So we end up with 2 solutions here for that last for that rational function. So we're dividing by 0 twice, when x is -1 and when x is +1. So we're going to throw those out. All right. So now we want to kind of put all of this together. And we want to figure out what are the x values that fall inside all 3 of these different domains. And that'll give us the domain of our original function f of x, or the entire function f of x. So to help picture this, let's draw the x-axis. There it is. There's our x-axis. And let's start with, well, let's put 0. Let's plot the origin there in the middle. And let's start with inverse tan. Let's sketch what inverse tan, the domain of that, looks like. And it's all real numbers. So we're just going to go right across. Domain of inverse tan covers up the entire x-axis. Now, what about the domain of 3 times natural log? Well, that's only the positive numbers, and it's this open parentheses at 0, so we got to throw 0 out of our domain. So let's put an open dot at the origin there to indicate that we're not going to include that point, and then we're looking at all positive numbers going forward. Then for our rational function, same thing. We have the entire x-axis with these 2 exceptions. So let's plot those 2 exceptions. We've got -1 and then +1. And we've got to exclude those. So let's put our open dots, meaning exclusion. But everything else is okay. So everything here we want to include in our domain for that rational function. Everything in between those 2 x values we want to include, and then everything beyond 1 we want to include. I'm just going to slide that down. Nope. Let's see. There we go. That was bugging me. All right. So now we want to see which out of the entire x-axis, which x values line up with all 3 of these different domains. So over here won't work. Any of these x values over here won't work because there was nothing for 3 natural log x. So we got to throw out all those values over here. 0 isn't going to work because this point is excluded, so we got to throw that one out. And 1 is going to be excluded because we had to throw that point out. So if we line everything up, we're able to figure out the domain of our original function f of x. And it's everything in this stretch in between 0 and 1, except we can't include 0 because that one point was missing, and we can't include 1 because that other point was missing. So it's going to be the interval from 0 to 1. And then if we line things up, kind of look onto the other side of x equals 1, all of these x values do cover up all 3 of those. So we want to include everything from 1 onward. And we put a little union symbol in the middle there to indicate that we're kind of stitching those two different intervals together. So this is the domain of our original function, and that means our original function is continuous on these intervals. So we'll call this also the domain of continuity. So at any x value in this interval, or in these two intervals, our function's continuous at it. All right, so just a little bit of practice there, figuring out when a function is, what its domain is, and then extending it a little bit further and knowing now that, well, it's also going to be continuous. So there's not going to be any jumps, breaks, or holes in the graph on this interval, and there's not going to be any jumps, breaks, or holes in the graph when we plot the function on this interval. Now, I do want to go back. There's one example that I want to finish up. And now this, we were looking at example 5 at the end of last class. And this is something a little bit different. So this is not an elementary function. This is a piecewise function. So yeah, parts of it are rational functions. But then we have these certain conditions on it, like this. So this one we have to check the continuity going back to our limit definition. So if we remember, there's really 3 things we need to check. We need to check our function value at the x value we're interested in. And then we also have to check the left-hand limit of our function. And we also have to check the right-hand limit of our function as our x value gets closer to that number we're interested in. All right, so we already found our function value at 3 in this case was equal to 0. So for the directly evaluating this function, we're looking at x equal to 3. We go up to the different pieces of our function, find the condition that's satisfied. So when x is 3, we use this formula. Now for our left-hand limit, let's start with that one next. So for our left-hand limit, we're interested in x approaching 3 from the left. And that means we're going to be using values that are close to 3 but a little bit smaller. So we're going to be using values x that are just slightly smaller than 3. And we need to figure out which piece of our piecewise function to use. So if we go back up, we've only got 2 conditions. This one only tells us when x is equal to 3. This one tells us when x is not equal to 3. So x, that covers x being less than 3. So we're going to use, well, this condition satisfied for the left-hand limit. So we're going to use this as our formula for f of x. So we're going to fill that in for f of x. Fill in the correct formula based on our pieces. All right, so now this is just a regular limit that we've been practicing. So first thing to try is direct evaluation. So we're going to try direct evaluation at x equals 3. Now, when we plug 3 into this formula, what do we get? Well, we get 1 over 3 minus 3, which is 1 over 0, which is a c over 0 form. So that's the first thing. We identify that this is a c over 0 form. So now we kind of know what to expect. We want to recognize, what does a c over 0 form actually tell us? And let's state it. That means, kind of in step 2 here, that means we're going to have an infinite limit. So we have 2 choices, plus infinity or minus infinity. And we got to figure out which one. So we got to use a test number to do that. And that's the kind of the final step here for an infinite limit. So first, if we recall, for an infinite limit, figure out first that it's a c over 0 form. Recognize what that means. So it means it's going to be either plus infinity or minus infinity. And then we're going to use a test number to figure out, are the values of this formula getting large positive or negative? So x is approaching 3 from the left. So that means the values of x are going to be close to 3, but just a little bit smaller. So a good test number for the left side would be 2.9. So something close to 3, but subtract a little bit. We're going to plug that in to the formula here, and we end up with 1 over 2.9 minus 3. And when we simplify, we end up with 1 over negative 0.1. And we don't really care what this number is, other than it's negative. So it's a positive number divided by a negative number. Result is negative. So that means negative infinity. Now, I won't go through it. It's good practice. But you should find that for the right-hand limit, this right-hand limit would be positive infinity. So similar first and second steps here. The only thing different is your test number. So you might try like a test number of maybe 3.1. But I recommend trying it out, because for infinite limits, these don't necessarily always have to be opposite. They might be the same. So there's no way just looking at the left side you'd be able to figure out what's going on the right side. All right, so what we've done is we've calculated our 3 different values. We've got our value directly at x equals 3. We've got our left-hand limit, and we've got our right-hand limit. And so to check for continuity, we just have to see, are these 3 numbers equal to each other? And, well, there's all sorts of things wrong here. So first of all, these 3 values are not the same. These things aren't even numbers. So there's all sorts of wrong here. So because the 3 values are not equal to each other, and some of them aren't even numbers, this thing is not continuous. So this is discontinuous at x equals 3, since, well, let's give a reason. Well, if we compare, all sorts of things we could say here, but if we look at the left-hand limit and the right-hand limit, these things don't match up, so the overall limit doesn't exist. So that's one thing you need for continuity. The overall limit has to exist, and in this case it doesn't. You might say, yeah, all 3 of these things don't match, discontinuous. Minus infinity is not a number, so we're not actually approaching a specific point on the left side. So, I mean, this is really enough to say that this function's discontinuous. All right. So we're going to stop there. And for the material that I wanted to make sure we get caught up with due to class today, and then we'll have I'll continue on with the rest of these notes in a second video. So I'll see you over there.